Deep within the dense heart of a star cluster, astronomers have uncovered a black hole that shouldn't be there, a celestial phantom that defies the very equations predicting its absence. For decades, scientists have puzzled over the disappearance of these cosmic giants from their birthplaces, assuming they either slipped into the void or merged silently. But Hubble's sharp eye has now detected one of the first missing black holes in a cluster where none should remain, rewriting the story of how these monstrous objects vanish. This discovery doesn't just fill a gap in the data, it challenges the entire framework of how star clusters evolve. Imagine a cosmic ballet where black holes are supposed to dominate the dance, yet one has slipped through the curtain unnoticed until now. This isn't just about missing stars, it's about rewriting the rules of gravity itself. In the vast expanse of the universe, where stars are born and die in cosmic dramas of light and gravity, there exists a hidden world of black holes, objects so dense that not even light can escape their pull. For decades, astronomers have studied these enigmatic entities, yet one mystery has persisted: where are the missing black holes in star clusters? Now, NASA's Hubble Space Telescope has made a groundbreaking discovery that brings us closer to solving this cosmic puzzle. For the first time, scientists have identified a black hole that was thought to be missing from a dense star cluster, offering a glimpse into the elusive nature of these invisible giants. To understand this discovery, we need to step back and explore the life cycle of stars and the remnants they leave behind. When massive stars reach the end of their lives, they collapse under their own gravity, forming either neutron stars or black holes. In dense star clusters, regions where millions of stars are packed into a relatively small space, these remnants should be abundant. Yet, observations have revealed a discrepancy: many of these black holes seem to be missing. This absence has puzzled astronomers for years, leading to the hypothesis that some black holes might be hidden in ways that make them difficult to detect. The star cluster in question, NGC 6397, is one of the oldest and most compact star clusters in our galaxy. Located approximately 7,800 light-years away, it is estimated to be around 13 billion years old, making it a relic from the early days of the universe. Such ancient clusters are expected to host a significant number of black holes, yet previous observations suggested that fewer than expected were present. This discrepancy led scientists to suspect that some black holes might be hiding in plain sight, obscured by the dense environment of the cluster. The Hubble Space Telescope, with its unparalleled ability to capture detailed images of distant celestial objects, has now provided the key to this mystery. By analyzing the motion of stars within NGC 6397, astronomers detected subtle gravitational effects that hinted at the presence of a massive, unseen object. These effects are similar to how we detect planets around distant stars by observing the wobble they cause in their host star's motion. In this case, the gravitational tug of a hidden black hole was influencing the movement of nearby stars, creating a pattern that could only be explained by the presence of a massive, compact object. What made this discovery particularly significant is that the black hole identified by Hubble is not one of the supermassive giants found at the centers of galaxies. Instead, it is a medium-sized black hole, with a mass roughly 3.5 times that of our Sun. Such intermediate-mass black holes are rare and their existence has long been debated. While some astronomers believe they could be the seeds from which supermassive black holes grow, others argue they may form through different processes. This discovery adds a new piece to the puzzle, suggesting that these intermediate-mass black holes might be more common in dense star clusters than previously thought. The challenge in detecting such a black hole lies in its invisibility. Unlike stars, which emit light, black holes do not shine on their own. Instead, they can be detected through their interaction with surrounding matter. In the case of NGC 6397, the black hole's gravitational influence on nearby stars provided the clue. By meticulously tracking the motion of stars within the cluster, the research team was able to infer the presence of the black hole. This method relies on the principle that massive objects distort the fabric of spacetime, causing nearby stars to orbit in ways that can be measured and analyzed. This discovery also raises intriguing questions about the formation and evolution of star clusters. If black holes are indeed more prevalent in these environments, it could mean that the dynamics of star clusters are more complex than previously understood. The presence of a large number of black holes might influence the way stars move within the cluster, potentially affecting the rate at which stars collide or merge. Such collisions could lead to the formation of new stars or even the creation of more black holes, creating a feedback loop that shapes the cluster's evolution over time. Moreover, the identification of this missing black hole has implications for our understanding of how black holes form and grow. While the exact mechanisms behind the formation of supermassive black holes remain a topic of debate, the existence of intermediate mass black holes like the one in NGC 6397 could provide crucial insights. Some theories suggest that these intermediate mass black holes might form through the direct collapse of massive gas clouds, while others propose they result from the merging of smaller black holes. The discovery of this particular black hole offers a rare opportunity to study one of these potential pathways in action. The significance of this finding extends beyond the confines of NGC 6397. It represents a step forward in our quest to understand the distribution and behavior of black holes across the universe. By identifying missing black holes in star clusters, astronomers can refine their models of how these objects form, evolve, and interact with their surroundings. This knowledge is essential for predicting the behavior of black holes in other environments, such as the centers of galaxies or the remnants of supernova explosions. As we look to the future, this discovery opens new avenues for research. Upcoming missions, such as the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope, will provide even greater sensitivity and resolution, allowing astronomers to probe deeper into the mysteries of black holes. These instruments will enable scientists to search for more missing black holes in other star clusters, further refining our understanding of their role in the cosmos. In conclusion, the discovery of the first missing black hole in NGC 6397 marks a pivotal moment in the study of these enigmatic objects. By revealing the presence of a hidden black hole, Hubble has not only solved a long-standing mystery but also provided valuable insights into the formation and evolution of star clusters. This finding underscores the importance of continued exploration and observation in unraveling the secrets of the universe. As we continue to peer into the cosmos, each new discovery brings us closer to understanding the invisible forces that shape our universe. For decades, astronomers have puzzled over a cosmic mystery: why do some star clusters seem to lack the expected number of black holes? These dense regions, where stars are packed tightly together, should be ideal places for black holes to form. Yet observations have repeatedly shown that the number of detected black holes is far lower than theoretical models predict. Now, a breakthrough has been made. NASA's Hubble Space Telescope has uncovered the first missing black hole in a star cluster, offering a tantalizing glimpse into the hidden universe. But how did scientists arrive at this discovery? The answer lies in a combination of advanced technology, meticulous observation, and a deep understanding of how black holes influence their surroundings. Let's walk through the process that led to this moment. The journey began with a fundamental question: where do black holes hide? Unlike stars, which emit light, black holes are invisible. However, their presence can be inferred through their gravitational effects. In a star cluster, the gravitational pull of a massive unseen object would subtly alter the motion of nearby stars. By studying these motions, astronomers can detect the presence of a black hole, even if it's hidden in the dark. But detecting such an object requires an instrument with extraordinary precision, something the Hubble Space Telescope is uniquely equipped to provide. Hubble's role in this discovery was critical. Launched in 1990, the telescope has spent decades peering into the cosmos, capturing images and data that have reshaped our understanding of the universe. Its ability to resolve faint details and measure subtle changes in stellar motion makes it an ideal tool for this kind of search. The team behind this discovery used Hubble's Advanced Camera for Surveys (ACS) and its Fine Guidance Sensors (FGS) to track the movements of stars within the star cluster. These instruments allowed them to measure the velocities of individual stars with incredible accuracy, revealing patterns that hinted at the gravitational influence of an unseen mass. The process of identifying a missing black hole is not straightforward. It begins with extensive observations. The team spent years collecting data on the star cluster, meticulously mapping the positions and velocities of thousands of stars. This required countless hours of telescope time, as each observation had to be precise. The data was then analyzed using sophisticated algorithms designed to detect anomalies in the motion of stars. If a black hole were present, it would cause a measurable deviation in the trajectories of nearby stars, creating a subtle wobble in their paths. However, distinguishing such a signal from other sources like the natural motion of stars or the gravitational pull of other unseen objects was a significant challenge. To confirm the presence of a black hole, the team had to rule out alternative explanations. For example, a dense concentration of stellar remnants, such as neutron stars or white dwarfs, could also exert a gravitational influence. The key was to determine whether the object in question was massive enough to be a black hole. This required precise measurements of the object's mass. Using Hubble's data, the team calculated the mass of the unseen object by analyzing how it affected the stars around it. If the mass was in the range expected for a black hole, typically several times that of the Sun, the case for its existence became stronger. But the discovery wasn't just about detecting a single object. It was about understanding the broader context of missing black holes in star clusters. Theorists had long speculated that many black holes might be hidden in these clusters, either because they were too faint to detect or because they had merged with other black holes over time. However, without direct evidence, these ideas remained speculative. The Hubble observations provided the first concrete confirmation that such missing black holes could exist, and that they might be more common than previously thought. The timeline of this discovery was as intricate as the process itself. It began with initial observations of the star cluster, which had been conducted over several years. These early datasets were used to build a baseline understanding of the cluster's dynamics. As the team refined their models, they identified discrepancies in the expected stellar motions, prompting further observations. Additional data was collected using Hubble's high-resolution imaging capabilities, allowing the team to zoom in on specific regions of the cluster where the gravitational anomalies were most pronounced. Each new dataset brought the team closer to a definitive answer, but the process was painstaking. Every measurement had to be cross-checked, and every assumption tested. One of the most impressive aspects of this discovery was the use of Hubble's ability to track the same stars over time. By capturing images of the cluster at different points in its orbit around the galaxy, the team could observe how the star's positions and velocities changed. This temporal data was crucial for identifying patterns that indicated the presence of a massive, unseen object. The precision required to detect these changes was extraordinary. Hubble's instruments had to measure shifts in stellar positions down to a fraction of a pixel, a feat made possible by its advanced optics and the stability of its orbit above Earth's atmosphere. Another key element was the collaboration between different scientific teams and observatories. While Hubble provided the critical data, other telescopes and instruments played supporting roles. For example, ground-based telescopes might have been used to gather additional data on the cluster's overall structure, while other space-based observatories could have contributed complementary information. This multi-instrument approach allowed the team to build a comprehensive picture of the cluster's environment, ensuring that their conclusions were robust and well-supported. The confirmation of the missing black hole also relied on theoretical models of star cluster evolution. By comparing the observed data with simulations of how star clusters should behave, the team could assess whether their findings aligned with existing theories. If the gravitational effects they observed matched the predictions of models that included hidden black holes, it strengthened the case for their existence. Conversely, if the data didn't fit, it would have prompted a re-evaluation of the models themselves. This interplay between observation and theory is a hallmark of scientific discovery, and it was central to this breakthrough. Despite the complexity of the process, the discovery itself was a testament to the power of modern astronomy. The ability to detect an object that has eluded direct observation for so long highlights the ingenuity of the scientific method. It also underscores the importance of long-term observational campaigns, where patience and persistence yield results that change our understanding of the universe. The team's work didn't just confirm the existence of a single black hole, it opened the door to a new era of research into the hidden populations of black holes in star clusters. Looking ahead, this discovery has far-reaching implications. It suggests that many star clusters may harbor a significant number of undetected black holes, which could influence the dynamics of these systems in ways we've yet to fully understand. Future missions, such as the James Webb Space Telescope and upcoming ground-based observatories, will likely play a role in further exploring this phenomenon. By combining data from multiple sources and refining our models, astronomers hope to uncover more of these hidden giants and shed light on the complex life cycles of stars and black holes in the cosmos. In the end, the journey to discover the first missing black hole was as much about the tools and techniques used as it was about the mystery itself. It was a reminder that even in the vastness of space, there are still secrets waiting to be uncovered, and that with the right technology, patience, and curiosity, we can bring them to light. NASA's Hubble discovers first of star clusters missing black holes. This part of our deep dive into NASA's Hubble discovers first of star clusters missing black holes focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, astronomers have been unraveling the mysteries of the universe, peering into the depths of space to uncover the secrets of stars, galaxies, and the invisible forces that shape them. Among the most enigmatic of these forces are black holes, regions of spacetime where gravity is so intense that not even light can escape. The concept of black holes wasn't always a scientific certainty. It began as a theoretical idea, born from the equations of Albert Einstein's general theory of relativity in 1915. At the time, Einstein's work described gravity as the curvature of spacetime caused by mass, but it wasn't until the 1930s that physicist Karl Schwarzschild calculated the existence of what would later be called a black hole, a point of infinite density where the gravitational pull becomes overwhelming. However, these ideas were largely dismissed as mathematical curiosities, not physical realities. It wasn't until the 1960s and 1970s, with the advent of radio astronomy and the discovery of quasars, that black holes began to take shape as a legitimate scientific phenomenon. Observations of massive, luminous objects at the centers of galaxies hinted at something unseen, something with gravity so strong it could explain the extreme energy outputs. By the 1970s, the term black hole had entered scientific discourse, and the idea that these objects could exist in dense stellar environments began to take root. But even as astronomers began to accept black holes as real, the question of where they might hide remained. Star clusters, dense collections of stars bound together by gravity, became a focal point for this mystery. These clusters, some of which are millions of years old, are laboratories for studying stellar evolution and the dynamics of massive systems. Yet, within these clusters, something seemed amiss. Observations revealed a discrepancy. The total mass of stars in these clusters didn't add up to what was expected based on their luminosity. There was a gap, a missing mass that couldn't be explained by visible matter alone. This led to the hypothesis that something unseen, perhaps a population of black holes, could account for the missing mass. However, detecting these elusive objects proved to be a monumental challenge. Black holes, by their very nature, don't emit light, making them nearly impossible to observe directly. For decades, astronomers relied on indirect methods, such as detecting the gravitational influence of black holes on nearby stars or the X-ray emissions from accretion disks around them. But in star clusters, where stars are packed closely together, these signals can be drowned out by the sheer density of stellar activity. The search for missing black holes became a puzzle, one that required not only advanced observational techniques but also a deep understanding of how these objects might behave in such environments. The quest to solve this puzzle has been a long one, spanning decades of scientific inquiry. Early missions like the Hubble Space Telescope, launched in 1990, played a crucial role in advancing our ability to study these distant systems. Hubble's high-resolution imaging and spectroscopic capabilities allowed astronomers to peer into star clusters with unprecedented clarity, revealing details about their structure and dynamics. However, even with Hubble's power, the missing black holes remained elusive. The challenge lay in distinguishing between the gravitational effects of black holes and other phenomena, such as dark matter or the influence of neutron stars. Over the years, researchers developed new methods to probe these clusters, including analyzing the motion of stars near the centers of clusters to infer the presence of unseen masses. These studies hinted at the possibility that a significant fraction of the missing mass could indeed be black holes, but definitive proof remained out of reach. The breakthrough came with a combination of technological advancements and a deeper understanding of the physics at play. The Hubble Space Telescope, now in its third decade of operation, has been instrumental in refining these observations. Its ability to capture detailed images of star clusters has allowed scientists to study their internal structures and the distribution of stellar velocities with greater precision. By analyzing how stars move within these clusters, researchers can infer the presence of unseen masses. The latest discoveries, including the first confirmed detection of a missing black hole in a star cluster, represent the culmination of decades of effort. This achievement not only validates the long-standing hypothesis about missing black holes but also highlights the power of modern observational astronomy. The journey to uncover these hidden giants has been one of perseverance and ingenuity, driven by the relentless pursuit of knowledge. As scientists continue to refine their techniques and expand their observations, the story of black holes and star clusters is far from complete. Each new discovery brings us closer to understanding the full extent of these enigmatic objects and their role in the universe's cosmic tapestry. The discovery of a missing black hole in a star cluster by NASA's Hubble Space Telescope has opened a new chapter in the quest to understand the hidden lives of these cosmic giants. But while this finding is a breakthrough, it also raises more questions than answers. For decades, astronomers have puzzled over a fundamental mystery: where do the black holes in star clusters go? These clusters are dense, ancient collections of stars, yet their populations of black holes seem to be missing. Now, with the first confirmed detection of such a missing black hole, the search for the rest of the missing population has begun. But the answers remain elusive, and the science is far from settled. Let's explore what this discovery tells us and what it still leaves unanswered. Star clusters are among the oldest and most densely packed regions in the universe. They form when vast clouds of gas and dust collapse under gravity, giving birth to thousands of stars in a relatively small volume of space. Over billions of years, these clusters evolve, with stars colliding, merging, and eventually dying. But black holes, some of the most enigmatic objects in the cosmos, have long been a puzzle. These dense, gravity-warping remnants of massive stars should be abundant in such environments, yet observations reveal a discrepancy. Astronomers have predicted that star clusters should host hundreds, even thousands, of black holes. But when they look, they find far fewer than expected. This gap in the data has led to a decades-long mystery: where have these black holes gone? The discovery of this particular black hole in the ancient star cluster NGC 6397 is a significant milestone. Located about 8,500 light-years from Earth, NGC 6397 is one of the oldest known star clusters, estimated to be around 13 billion years old. Its age and density make it an ideal laboratory for studying the evolution of stars and black holes. But even in such a dense environment, black holes are difficult to detect. Unlike stars, which emit light, black holes only reveal themselves through their gravitational effects or the radiation they emit when they consume nearby matter. This makes them elusive, especially in crowded star clusters where their signals can be drowned out by the light and motion of surrounding stars. The Hubble discovery, however, suggests that some of these missing black holes may not be as hidden as once thought. By analyzing the motion of stars within the cluster, astronomers were able to infer the presence of a black hole whose gravitational pull is subtly altering the trajectories of nearby stars. This method, known as dynamical mass modeling, has allowed scientists to indirectly detect black holes in star clusters for years. But the fact that this is the first such detection in a star cluster raises the question: why has it taken so long to find even one? One possibility is that black holes in star clusters are not as numerous as previously thought. But this seems unlikely. Theoretical models predict that massive stars, those with more than 8 times the mass of the Sun, should collapse into black holes after they exhaust their nuclear fuel. In a star cluster, these black holes would be expected to form in the densest regions, where gravitational interactions are strongest. However, simulations suggest that many of these black holes may not remain in their birthplace. Instead, they could be ejected from the cluster through a process known as gravitational interactions. When a black hole encounters another massive object, such as another black hole or a neutron star, it can exchange energy and momentum, gaining enough velocity to escape the cluster's gravitational pull. This phenomenon, called dynamical ejection, could explain why some black holes are missing from star clusters. But if this is the case, where do they end up? Do they wander the galaxy as isolated, rogue black holes, or do they eventually merge with other black holes or stars? Another theory proposes that the missing black holes are not missing at all, they are simply hiding in plain sight. Some astronomers suggest that the black holes in star clusters may have merged with other black holes or neutron stars, forming larger, more massive objects. These mergers would release powerful gravitational waves, which could be detected by observatories like LIGO and Virgo. However, the absence of such signals in the data has led some to question whether this is the correct explanation. Moreover, if black holes are merging within star clusters, their combined mass should leave a detectable imprint on the cluster's dynamics. Yet, observations have not revealed the expected signatures of such mergers. This suggests that either the mergers are rare, or the black holes are not behaving as predicted. The discovery of this missing black hole in NGC 6397 adds a new layer of complexity to the puzzle. The black hole detected by Hubble is relatively small, with a mass estimated to be about 10 times that of the Sun. This is significant because it suggests that the missing black holes in star clusters may not all be the massive, runaway objects previously assumed. Instead, they could be a mix of small and large black holes, each with different fates. Some may be ejected from the cluster, while others may remain hidden within its depths. This diversity in black hole populations challenges existing models and highlights the need for more detailed observations. However, the question remains, how can we confirm the presence of these missing black holes if they are so difficult to detect? One approach is to look for indirect evidence. For example, if a black hole is ejected from a star cluster, it could pass through the galactic halo, or it might interact with other stars or dark matter. These interactions could generate detectable signals, such as X-ray emissions or gravitational waves. Additionally, if a black hole merges with another black hole or a neutron star, the resulting explosion of energy could be observed as a burst of gravitational waves. However, the challenge lies in distinguishing these signals from other cosmic phenomena. The universe is filled with events that produce similar signatures, making it difficult to isolate the specific contributions of black holes in star clusters. This uncertainty underscores the limitations of current observational techniques and the need for more advanced instruments. The search for missing black holes also has broader implications for our understanding of black hole formation and evolution. If a significant fraction of black holes in star clusters are missing, it could mean that our models of stellar evolution are incomplete. For example, some theories suggest that black holes may form in binary systems, where two stars orbit each other before one collapses into a black hole. In such cases, the black hole could be pulled into a tight orbit with its companion, forming a binary black hole system. These systems are thought to be the primary sources of gravitational waves detected by LIGO and Virgo. However, if many of these binary systems are disrupted or ejected from their host clusters, it could affect the overall population of gravitational wave events. This raises the question, how many of the black holes we've detected through gravitational waves are actually the result of these disrupted systems, and how many are the result of other processes? Another angle to consider is the role of dark matter in the fate of missing black holes. While dark matter itself does not interact with electromagnetic radiation, it does exert gravitational influence. Some astronomers speculate that dark matter could play a role in shaping the dynamics of star clusters, potentially influencing the motion of black holes and their interactions. However, this remains a speculative idea, as dark matter's properties are still not fully understood. The interplay between dark matter and black holes in star clusters is an area of active research, but it is far from settled. The discovery of this missing black hole does not provide direct evidence for or against this hypothesis, but it does highlight the need for more detailed studies of the dark matter environment in such clusters. Despite the challenges, the discovery of this missing black hole offers a tantalizing glimpse into the hidden universe of black holes. It suggests that the search for these objects is not just about finding them, it's about understanding the complex processes that govern their behavior. The fact that this is the first such detection in a star cluster hints at the possibility that many more are waiting to be found. But the path to uncovering their secrets is fraught with uncertainty. Each new discovery brings new questions, and the answers may lie in the most unexpected places. For example, the study of gravitational waves, the observation of star cluster dynamics, and the analysis of stellar populations could all contribute to solving this mystery. However, the answers may not come easily. The universe is vast, and its secrets are often hidden in the most subtle of clues. As we continue to refine our observational techniques and expand our understanding of black hole physics, the mystery of missing black holes in star clusters will likely persist. But this is the nature of scientific discovery, each answer leads to more questions. The discovery of this black hole by Hubble is a significant step forward, but it is also a reminder that the cosmos still holds many mysteries. The search for the missing black holes is not just about finding them, it's about unraveling the fundamental forces that shape the universe. And in doing so, we may gain new insights into the nature of gravity, the life cycles of stars, and the intricate web of interactions that govern the cosmos. For now, the missing black holes remain a mystery, but their presence in the data suggests that the answers are out there, waiting to be discovered. NASA's Hubble discovers first of star clusters missing black holes. This part of our deep dive into NASA's Hubble discovers first of star clusters missing black holes focuses on explain what's coming next, future missions, instruments, or observations that could confirm, extend, or challenge what we know so far. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. NASA's Hubble discovers first of star clusters missing black holes. This part of our deep dive into NASA's Hubble discovers first of star clusters missing black holes focuses on briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.